Good morning, this is Dr. Turner for Integrated Math 2. Today we're looking at 9.4. 9.4 is looking at change in dimensions. Change in dimensions specifically of two-dimensional and three-dimensional shapes. Now this is something if you took fundamental math with me where we talked about unit conversions and how the unit conversions in two and three-dimensional shapes is different than conversions in one-dimensional shapes. And so that's essentially what we're talking about here with changes in dimensions. But we're not going to assign units to these. It's just how much is the area or perimeter or volume changing based on a change in dimensions. Okay, so we'll go ahead and get started here. Let's say I take a square or a rectangle, and I ask you something like, if I double the length of this rectangle, how does the volume change? Right? So we should know by now that if I'm looking at the area of a rectangle, that is given as length times width. Okay? So if I were to double the length of the rectangle, the question is, well, how much would the area change? Now there are a few ways you can do this. You can use a visual representation, or you could look at the formula. But if I were to double the length, let's say, and again this is not necessarily to scale, but let's say I doubled the length. The question is, well, how much more space is that rectangle occupying compared to the original? And we can kind of see, if I were to, let's say, take this rectangle and see how many I could fit in this new rectangle, well, yeah, that's about 2. So it's occupying twice the amount of space as the original. We can also see that in the formula itself. If I were to replace the length, it doesn't matter what the number is, if I replace the length with double that, then compared to the original area, it's double. So we can see that visually, and we can also see that in the formula itself. And that's essentially what you're doing here in this assignment, is comparing how does the change in a dimension change either the area or the surface area or the volume of a shape. Now, if the dimension is one-dimensional, let's say length, for instance, then the change in dimensions is going to match the change in area or perimeter or surface area. However, when you look at something that is non-linear, let's say we look at a circle, for instance, and let's stick with area for now. Let's say an area, of course, for a circle is pi times radius squared. Okay. Let's say I double the radius. Question is, what is the change, or how did the dimensions change for area? Now, again, you can do this visually, or you can do it with the formula. But if I were to, let's say, double the radius, and again, this isn't necessarily to scale, but let's say something like that. That's about doubling my radius. And let's do the same test that we did with the rectangle. If I take this circle, okay, well, I can definitely fit more than just 2 circles inside this larger circle, right? So the one-to-one that we had with the rectangle doesn't work here. And the reason for that specifically is because in the area formula, the radius is being squared. So if the variable is squared or cubed, then the change in dimensions is going to be in proportion with that exponent. So algebraically, what that looks like, if I were to take the area here, and it doesn't matter what the number is, but if I change the radius to twice the radius, right? Well, 2 squared, that gives me 4 pi r squared. So I would take the change in dimension, apply the exponent. So if I double the radius, the area of this circle would be 4 times bigger, not 2 times bigger. So pay attention to, is the variable being raised to an exponent or not? If it is being raised to an exponent, then it's not going to be a one-to-one change in dimensions. Okay. Now both of these examples are of where the shape is getting bigger, but the same is going to be true if the shape is getting smaller. You can look at it. You can look at it in a diagram, or you can look at it in terms of the equation. You should be able to come to the same conclusion. So let's do a three-dimensional shape now. Let's say I have a cube. We'll start out with, let's do a square. Okay, so if I have a square, area of a square, you could think of it as a rectangle and still get the same answer, but you don't have to. Let's say the area of the square is side length squared, because it's a square, not a rectangle technically. And let's say I take the side length and I divide it by half. Okay. Now, because this is a square, all the side lengths are the same. So if I were to cut the side length in half, again, taking a little square compared to the big square, this would be half. Okay. Looking at that formula, if I change the side length to be half of whatever the side length is, squared, then this is s squared over 4, or 1/4 s squared. And we can see that visually. If I take this smaller square, right, I can fit 1, 2, 3, 4 squares inside that larger square. So whether the shape is getting, the change of dimension is making the shape bigger or smaller, the same is going to apply. All these rules apply to both 3 and 2-dimensional shapes. You want to pay attention again to what variable is being changed. So let's take something like a cylinder, and let's look at volume. Volume of a cylinder is area of the circle, pi r squared, times the height. So here's my radius, here's my height. Okay. Now, again, what changes the volume in this case is going to be dependent on which variable I'm changing. So if I were to, let's say, double the height, and you can do this again visually, or you can do it algebraically, but if I were to double the height, okay, the circles wouldn't change. Those would be the same, more or less, bear with me. But if I were to double the height, right, the question is, well, how much more space is this new cylinder occupying? And I could click and drag like I did in the previous examples, but it's taking up approximately twice the volume. So doubling the height would mean I'm doubling the volume. Looking at the variable, there's no exponent there, so it's a 1-to-1 change. However, if I were to, let's say, triple the radius, okay, well, now tripling the radius, making that radius 3 times bigger, even if the height's the same, okay, I can fit more than 3 cylinders in this larger space. Again, trying to make the best of looking at a 3-dimensional concept in a 2-dimensional space. But we'd have something like this, right? Going from here to here, going from here to here. And again, if I were to click and drag, roughly, my original cylinder here, right, I can fit more than 3 cylinders in here, right? So that change is because in the formula, the radius is being squared. So algebraically, if I change the radius to be 3 times bigger, okay, that would result in a change in volume that is 9 times bigger. So if the variable that's being changed doesn't have an exponent, it's a 1-to-1 change in dimensions. And if the change in variables has an exponent, then it's going to be that original dimension change squared or cubed, depending on the formula. But that's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day, and I'll talk to you soon. Bye.